Swayam Prabha. Digital India. Educated India.
Morning. So, welcome back. We will continue our discussion of three-phase power circuit. So, last time we had discussed star connection for a balanced three-phase system. We will today first do delta connection of a three-phase system, and subsequently then we will do some problem solving, mostly involving unbalanced circuits, both balanced and unbalanced circuit. Okay. So, let us begin with delta connection of three-phase power circuits today. We did star connection of the three-phase circuits in the previous class, where we saw that the line voltage becomes root 3 times the phase voltage in a balanced circuit, and the line current is same as the phase current, and the power expression we got the power expression as P equal to root 3 VL cos phi. This is for three phase power, and Q equal to root 3 VL sin phi. Now, today we are going to show that the same thing happens as far as the power expression and Q expression are concerned. This is for a star connection. For a delta connection, the power expressions remain the same, but the current and the voltage expressions take a dual form. So, for delta expression also today balanced again, I am going to show that P 3 phase is still root 3 VL cos phi, and Q 3 phase is still root 3 VL sin phi, but the phase voltage is equal to line voltage here, and the line current here is going to be root 3 times the phase current. So, you can see the variation, just the dual of the other one. So, let us to derive this now today for the delta connected load. Let us first start with a balanced delta connected So, let us start with a balanced delta connected load. Sometimes you try to do a better figure and it becomes a worse figure. So, it is better to accept whatever figure you have, because it serves our purpose of explaining the concepts, and just move on with C, or if we want we can make it R, make it Y, and B. So, we have this three phase load, a three phase supply, and the supply is balanced. So, I am going to have this as my VAB. The VBC is going to lag the VAB by 120 degrees. It will be equal in magnitude, and this is going to be my VCA. So, I am going to have VBC as A square times of VAB and VCA as A times of VAB, where A is an operator which indicates 120-degree rotation in the anti-clockwise direction. Now, with respect to A to neutral and B to neutral, this is what VAB means, this is what VBC means, and this is what VCA means. It is the voltage A to B is if there is a neutral somewhere, this is how we will understand it. If we do not see a neutral anyway for this 3-phase supply, we know that with VAB should be interpreted as voltage of A taking B as reference, VBC should be thought of as voltage of. So, for the first one VAB is this, the second one VBC is voltage of B taking C as reference, and this is voltage of VCA is the voltage of C taking A as a reference. If there is a neutral, that means if this source I knew is a star connected source and so on and so forth, then I can come with this kind of a interpretation. Otherwise, this is a generic interpretation which is anyway valid, and because it is balanced, the magnitude of all of these three are same, and this is the convention of the angles. The 120-degree symmetric displacement is going to be like this. Now, because I am saying that system is balanced, so let us all these three impedances are same, and so the phase current in this is I1, let us say, which is current from A to and then going back towards going out like that. This is the current for the phase current for the other one I2, and this is the phase current for the third impedance, which I am going to call as I3. This is IA, IB and IC. These are line currents. This is line current, first line current, second line current and the third line current. So, these are the three line currents which I am having. So, what now where does this impedance Z come along? It comes along the phase AB. So, let us say that it draws a current I one which lags by an angle phi, with respect to VAB. Now, so the Z, the complex impedance Z in polar form is its magnitude is Z and its angle is phi, something positive is assumed. That is why I have said that the current that it is drawing, which is the magnitude will be VAB by Z, will be taking VAB as reference, will be a lag of minus a lag of 5 degrees, which is what I have drawn here. Similarly, the I2 will lag VBC by an angle of phi, and magnitude of I1 and I2 will be same, because this is my I1, I2 is going to be VBC by Z, and this will lag VBC phasor by an angle of phi. So, its angle is going to be minus 120 degrees minus phi, which is what I have shown here, minus 120 degrees, this is minus 120 degrees minus phi, and the third current I3 also follows in the same way, will lag VCA by an angle of phi, will also lag the VCA by an angle of phi. Let us take this picture out, it is getting a bit messy. So, let us paste it here. So, now these are my 3 I1, I2 and I3, they are equal in magnitude and again phase shifted by 120 degrees. So, I3, just to complete this, is magnitude is going to be VCA by Z, and since VCA has an angle of 120 degrees and the current has a and the impedance has an angle of 5 degrees. So, therefore, it lags the VCA phasor by an angle of phi. Okay. So, now let us look at what are my currents IA, the 3 line currents IA, IB and IC. So, IA is going to be equal to I1 minus I3, is it not? IA and comes here, it should flow out of these 2 branches. On this branch it flows out as I1, on this branch it will flow out as minus I3, because the incoming into the node is I3. So, the outgoing from the node is minus I3. So, the 2 outgoings from this node are I1 and minus I3. You sum those 2 outgoings, it should be equal to the incoming IA. Therefore, IA is equal to I1 minus I3. Similarly, IB will be I2 minus I1. IB is going to be I2, I1 is incoming. So, minus I1 is outgoing, this outgoing is I2. So, I2 minus I1 is going to be equal to IB, and IC will be sum of the outgoing I3 and the outgoing minus I2, because I2 is incoming. So, therefore, it is going to be equal to I3 minus I2. So, interestingly, if I sum IA plus IB plus IC in a balance in a delta circuit, what is it that I am going to get? This I2 will cancel, this I1 will cancel, this I3 will cancel, and I will get this to be 0. This is nothing to do with balanced or unbalanced. This is algebraic summation. I have not made any assumption of it being balanced or unbalanced. So, therefore, this is always true. This is always true that the phasor the summation of the 3 line currents IA, IB and IC will be 0. Now, let us focus on the balanced system perspective. So, in the balanced system perspective, I2 is lagging I1 by 120 degrees, In other words, leads by 120 degrees and another 120 degrees. So, if 120 degrees is lead is rotation is shown by A operator, then it becomes A square. So, therefore, I can write I 2 as A square times I 1 and I 3 leads I 1 by 120 degree. So, therefore, I should write it as A times of I 1, where A is a 120 degree rotational operator as shown above. So, with this, can I now write expression for I A? I A is I 1 minus I 3 from above, and substituting for I 3 as A times of I 1, I get this as 1 minus A times of I 1. So, that is I am sorry, this is this is I A, correct. I A is the A subscript here is phase subscript and the A here is the complex operator here. So, sometimes we will have this overlapping notations, can't help it. I B is equal to I 2 minus I 1, but I 2 is A square I 1 minus I 1. So, therefore, A square minus 1 times of I 1, and I C is equal to I 3 minus I 2. So, I 3 is A times I 1 and I 2 is A square times I 1. So, therefore, A minus A square times of I 1. So, now let us evaluate each one of them, and I will carry this figure below for our use. You can very clearly see that I 3 is A times of I 1 and I 2 is A square times of I 1. So, this is what I have used I 1 minus I 3, I 1 minus I 3. So, 1 I 1 minus A times of I 1 is 1 minus A I 1, I B is I 2 minus I 1, I 2 is written as A square I 1 minus I 1 is A square minus 1 I 1, and I C is I 3 minus I 2. So, I 3 is A times of I 1 and this is A square times of I 1. So, therefore, A minus A square times of I 1. So, we see this now. Now, let us look at first of all what is this 1 minus A. Let us do it geometrically. So, let me say that this is my 1 operator. Okay. So, then the A operator, the 120 degrees rotation is this operator, both of them have unit length. So, if I do minus of A, so the same thing will be have to be projected here, will become minus of A, and now you are doing summation of 1 plus minus of A, that is what 1 minus A means. So, you can apply the phasor summation, which is to say that pick this fellow, place him on the tip of the arrow here and calculate this new length. So, what should I be doing? I should be, I am basically doing parallelogram law of identity, but what I am going to show it to you is, just draw this. Or you can place it anywhere like this also, it is okay. So, now what I will do is, I will project, I will draw this perpendicular here. Since this is 120 degrees, so this is 60 degrees. Since this is 60 degrees, this is 30 degrees and this is also 30 degrees. So, this one projected here becomes of length 1 cos 30 degrees. So, 1 cos 30 degrees is going to be root 3 by 2, and by symmetry this one is also root 3 by 2, because this is 1, this length is 1 and this angle is also 30 degrees, it being a isosceles triangle. So, this length is also root 3 by 2. So, therefore, this whole length, I am sorry, this whole length is going to be equal to root 3. Is it not? This whole length is going to be equal to root 3. So, 1 minus a is root 3, and it lags one angle 0 phasor by 30 degree. So, therefore, e to the power minus j pi by 6. So, therefore, e to the power minus j pi by 6. So, 1 minus a is nothing but root 3 at an angle of minus of 30 degrees. So, therefore, this now can be written as root 3 times of I 1, and the line current lags the phase current by an angle of minus 30 degrees. Okay. Now, what about the, let us take this I b, which is same as a square minus 1 times of I 1. So, what about this? For 1, I will substitute a cube, because a is a rotation of 120 degrees. So, 3 times you do it, you will get 360 degrees, which is coming back to the original position, which is 1 angle 0. So, therefore, I can write this as the I 1, but then I take a square common and I will get 1 minus a times of I 1, but what is 1 minus a times of I 1? It is the I a. So, therefore, I get that the B, the line current in the B phase lags the line current in the A phase by 120 degrees, leads by 240 degrees or lags by 120 degrees. Now, let us, this is the power of A operator, you can very quickly algebraically do things. I c is, I am sorry, I c is a minus a square into I 1. So, I c is a minus a square into I 1. So, take a common, you get 1 minus a times of I 1, but 1 minus a times of I 1 is nothing but the line current in A phase. So, therefore, the line current in the C phase leads the line current in the A phase by 120 degrees, otherwise it is equal in magnitude to the line current in A phase, which itself is root 3 times the phase current. So, everything is perfect, we have really done a good job. So, good job so far. Now, let us try to assimilate our understanding. In the delta circuit, line current is balanced, of course, this is all for balanced thing is root 3 times the phase current, and the line voltage is same as phase voltage. Just take you back once more to the figure to see that the line, this is the phase voltage, this is the phase load, this is the voltage across it is the phase voltage, it is same as the corresponding line voltage. So, this phase voltage is correspondingly same to this line voltage. This phase voltage is correspondingly same to this phase voltage is correspondingly same to this line voltage which I have marked. So, that is one thing, and the line current becomes root 3 times the phase current magnitude wise. So, with this understanding, now let us look at the 3 phase power. 3 phase power is going to be 3 times the power per phase. So, power per phase is 3 times V 1 I 1 cos phi. If I take the first phase as the starting point, because the power which is dissipated in the first phase is the same as the power dissipated in the second phase and then the power in the third phase, and similarly I can write because it is a balanced circuit. But now these are actually speaking magnitudes. Let me see if I draw that, and then now I will use the fact that root 3 times phase voltage and line voltage are same, but root 3 times the phase current is the line current. So, I will just write this as root 3 V L I L cos phi, and this similarly is root 3 V L I L sin of phi. So, our objectives that we set forth at the beginning of this class to show that similar relationships exist with balanced delta connection, balanced system, but delta connected, we have achieved that. So, I think let us do some problem solving now, and our problem solving I am going to do both for balanced circuit as well as unbalanced circuit. So, the first problem that I have here, is in a 3 phase 4 wire system, the line voltage is 400 volts. So, if the line voltage is 400 volts, first of all just this is our standard supply, the phase voltage to phase voltage, which is voltage of a phase to the neutral, will be 231 volts. Resistive load of 2.3 kilowatts, 2.310, 3.465 kilowatts and 1.155 kilowatts are connected between the line conductors and the neutral. So, there is a neutral also, the supply is star connected very clearly. Calculate line currents and current in the neutral conductor. So, let us draw the circuit first of all. I will draw a star connected supply first. So, this is my star connected balance supply, this is V A to N, this is V B to N, this is V C to N. Actual supplies will be boxes or something like that, or terminals in your board, but for our ease of understanding I am drawing it as 120 degree apart, but actually they are 120 degree apart, or rather T by 3 time period apart when you see their waveforms on the oscilloscope, that is where actually you will see it. But because phasors have phasors are essentially vectors, we like to keep our understanding concept straight, we like to draw it like that. So, the mind background assimilates, oh, this one is 120 degree apart, but it is not in space actually, it is actually whatever is happening in the time domain. So, even if I draw VAB, VB is 3 horizontal lines and write this supply, but say they are balanced 3 phase supply, you should still take VBN as VAN at an angle of minus 120 degree and VCN as VN leading by an angle of 120 degree. It should not make any difference how I draw it on the actually on the paper, because I am not they are just supplies, I am just showing sinusoidal boxes and writing V A to N, B to N and C into it. But if I draw it balanced like that, then the communication is improved. That is what is why I am drawing it in this particular way. Okay. In a 3 phase 4 wire system, so the 4 where is the, so the 3 wires which you are getting, so these are the supply wires. Let me these are your supply wires, and there is a 4th wire. What is that 4th wire? Neutral conductor. So, let me draw neutral conductor a bit thick just to differentiate it, otherwise everything looks same. This is a neutral conductor. This is A phase, this is B phase, this is C phase. Now, what is it? You are given 3 resistive loads from A phase to neutral, B phase to neutral and C phase to neutral, connected between line conductors and neutral. So, let me draw loads using this is my first load, oops, my second load, and this is going to be my third load. Good. Now, what are these load values? They are given in kilowatts. So, let me write this as 2.310 kilowatts. The second one is 3.465 kilowatts and 1.155 kilowatts. I have chosen some nice numbers. You will see why I chose these odd kilowatt numbers, because then the currents are going to turn out to be nice numbers to simplify our calculation. Now, calculate the line currents. So, we need to calculate this IA, this IB. There doesn't flow anything, nothing flows further here. Okay, this is just shown like that, but it flows like this flows like this, and this will flow like this. If you want, I will shrink the arrows so that you feel comfortable. This is what is now, this is what is happening here. So, what is VAN, IAN? or IA. This is 2310 watts. What is VAN value? It is a resistive load. So, therefore, cos phi is 1 is 231, it is 231 volts. So, what happens to IA? IA becomes 10 amperes and angle 0. So, let me draw this. This is my VAN, this is my VBN, and this is my VCN. Being resistive loads across the 3 phases, IBN, IAN and ICN are going to be like this, but it is not balanced. Now, VBN into IB is equal to how much? These are I am just writing in terms of magnitude. The phasor diagram I have already sketched for you. This is 3465 watts, this is 3465 watts, and so IB will turn out to be 3465 watts divided by 231, and this is going to be 15 amperes, but at an angle of minus 120 degree. Why? This is because this is at an angle of 120 degrees. And what is going to be IC? IC is given to be, your load is 1155 watts divided by VC, which is 231 at an angle of VC is going to be 231, this is correct. I first look at the product of VBN into IBN. This is just I am looking at it as product magnitude of VBN into magnitude of IBN is equal to 3465, because the power factor is 1. So, therefore, the magnitude of IBN is 3465 by 231, which is 15 amperes, but then I know that it is in phase with VBN. So, therefore, I write it as minus 120 degree. I should not directly do I should not directly put this angle here. Similarly, IC is going to be equal to, magnitude of IC is going to be equal to the apparent power, because which is 1155 only, and power being this being a unity power factor load, volt amperes and watts are same, divided by the magnitude of VC, and this will turn out to be 5 amperes, and this should be, because it is a resistive load, it is in phase with VCN. So, therefore, it leads by 120 degrees. So, this is what is going to be IA, IB and IC. So, let us sketch it now. This is my 10 angle 0, 15 angle minus 120. So, somewhere here let me slightly longer, I should do it maybe this much. It is not actually 15 ampere, maybe this should be much less. Ten angle 0, 15 angle minus 120 degrees, maybe slightly. Minus 120 degrees, and IC is 5 amperes, so much smaller arrow, at an angle of 120 degree. So, let me sketch a vertical line as a reference here. So, now the neutral current is going to be I A plus I B plus I C. This is the neutral current. I A comes here, I B also joins here, I C also joins here, all of them return back from here, giving you a neutral current of I A plus I B plus I C, which is the neutral current I N. So, let us just calculate it. This is at an angle of 120 degree. So, this is 30 degree angle, and this is also at an angle of 120 degree. So, with respect to the vertical line, this is also going to be 30 degree angle. So, let us look at the horizontal component. So, the A phase gives you 10 amperes horizontal component, and the 15 ampere phase will give you, if you consider a line here, then this angle is going to be 60 degree. So, if I project it cos of 60 degree in this direction, which is the negative direction. So, therefore, I will get minus 15 cos of 60 degrees, and then this one when I project again, this angle is 60 degrees in the negative direction. So, 5 amperes also, minus 5 amperes, again cos of 60 degrees is half. So, therefore, this is 10 minus 20 into 1 by 2, which is 10 minus 10, which is equal to 0 ampere. This just turned out that this is 0 amperes, nice numbers, because I chose nice numbers, otherwise you would get something, nothing great about it being 0 amperes. Now, let us look at the vertical component. So, the vertical component is going to be equal to 10 amperes, I A is 10 amperes in the horizontal direction. So, therefore, it does not provide any vertical component. The vertical components are provided by these two. The first one, if I look at it, this 5 amperes into cos of 30 degrees. So, cos of 30 degrees will give me root 3 by 2, because I am projecting it here with a 30 degree angle. So, 5 ampere is the hypotenuse, base is cos of 30 degrees of that, which is 5 root 3 by 2 positive, and this one will give me 15 amperes cos 30 degrees. So, 15 amperes root 3 by 2, but in the negative direction. So, therefore, I will write this as minus 15 amperes root 3 by 2 in the negative direction. So, I get minus 10 root 3 by 2, which is minus of 5 root 3 amperes. So, what is the neutral current? Neutral current is horizontal component 0 plus j times the vertical component, which is this. So, the magnitude of the neutral current is going to be equal to 5 root 3 amperes, which is slightly less than 10 amperes, which would be slightly less than 10 amperes. You can calculate the value around 8 amperes, 8.5 amperes, that is what I expect that number to be. So, this neutral current, see, the moment you have got this unbalanced thing, this neutral current will flow through the neutral wire. Neutral wire has a resistance. It may be either equally thick as the phase conductor, if you are expecting a unbalanced supply, or normally if it is thinner also. If it is thinner, then the resistance will be more, and then it will suffer from I square R loss. So, you see that this causes the current unbalance, which causes current to flow in the neutral conductor, again makes your distribution system unnecessarily lossy, and that is a societal loss. We have talked about this earlier. So, balance is always useful, balance system operation is always useful in giving a efficient system operation. Okay. So, calculate the line currents, we have calculated all the 3 line currents, calculate the line currents and current in the neutral conductor. So, we are done with this problem. You see, simple enough, nothing great about it, but matter of detail we have to take care of each and everything. Now, let us take the next problem. A 3-phase delta connected load is shown below. Okay, this is the delta connected load which is shown below. Calculate the phase currents and the line currents. So, I have got 3-phase delta connected load is shown below. Calculate the phase currents and the line current. So, now 400 line voltage is 400 volts, VRY magnitude wise 400 volts, I will use angle 0. VBY, VYB, look at the tip of the arrow, that tells you how you should read it. So, the tip of the arrow is at Y and the bottom is at B, that means B is taken as the reference and Y is specified with respect to that is 400 this, and we know that in a balance supply this should be minus 120 degrees, and similarly the third one is VB with respect to R. So, VBR is again 400 volts and it should lead this by 120 degrees. So, these are the voltages which are given. So, let me draw them here. VRY, VYB, and VB. They are equal in magnitude 120 degree. I will remove these numbers here to keep. Maybe I will use some colors. So, make I will use slightly darker shade here. Okay. Now, let's look at the 3 currents I1, I2 and I3. These are the 3 phase currents. Now, across RY 100 ohm resistance comes. So, therefore, 400 divided by 100, which is 4 amperes, should be in phase with this is the current which is going to, which is the current I1. This is my current I1. Now, what about I2? I2 is an inductor of 100 ohms put across a supply of again 400 volts. So, 400 by 100, which is again 4 amperes, current should flow, 4 amperes current should flow for I2 also, but being inductor it will lag VYB by 90 degrees. So, therefore, I will have, this is 120 degrees, this is 60 degrees. So, therefore, this is also 60 degrees and somewhere here 30 degrees apart. I will have again I2 which is of 4 amperes, but it is at an angle of 90 degrees with respect to V y b. This is lagging V y b by 90 degrees. And now, let us look at the third current, which is flowing in this capacitor, which is having also magnitude wise all impedances are same. This is I have just taken it to ease the calculations, but it is not still balanced, because angle wise this will now lead the corresponding voltage V b to R by 90 degrees. The capacitance current leads. So, therefore, this is 120 degrees, I am sorry. So, 90 degrees from here. So, 120 plus 90 will give me 210. So, if I draw this vertical line at 180 degrees, then I will get 30 degrees coming here, which means that this current is again of 4 amperes. In this case, I 3 will also be 4 amperes, and if I sketch this vertical line down like this, you get 30 degrees. You get 30 degrees here and 30 degrees here. This is also 4. So now, I have got I 1, I 2 and I 3. Now, I know. So what is the calculate the phase current? So all the phase currents are known. Now our job is left is that to calculate the line currents. So what is the line current IR? Line current IR is I 1 minus I 3, and so I 1 is 4 amperes minus I 3. What is I 3? I 3 is also 4 amperes, but lagging the the voltage by 150 degrees. This is 150 degrees, and I y I am going to leave it to you to do the final set of computation. I 2 minus I 3, I 2 minus I 3 is going to be I am sorry, I 2 minus I 1. So, I 2 is 4 ampere and leading by 150 degrees. The 4 amperes leading by 150 degrees minus I 1, which is 4 amperes. Again I will leave to you to use your calculator and close the computation, or you can do it geometrically also, and I b is I 3 minus I 2. So, I 3 is 4 amperes lagging by minus 120 degrees, minus 150 degrees, minus of I 2, and I 2 is 4 amperes leading by 4 amperes leading by 150 degrees. Whatever these numbers are there, please punch them on your calculator and complete this computation. So, you basically need to do the phasor calculation to get the corresponding line currents, but the important thing that you would notice here is when you close your computation is that they are not balanced currents. With this, I think I will close this lecture here. Thank you.